by trying different sizes of things, we realized it should be really thin, should be light, it would have a stylus for drawing on it, wireless network, flat screen display, keyboard, and all that stuff. So this is kind of the thing I used to hold up back then of what computers should be like. It was kind of, if you could have what you wanted, what should it be like? And my image here was the children would be able to play collaboratively games on it, and especially games that they could make themselves. And I wanted for it to be able to do all the things you could do with a book, but be dynamic. So let's take a look now at how we might use the computer for some of this. And so the first idea here is just to show you the kind of things that children do. I'm using the software that we're putting on the $100 laptop. So they like to draw a little car here. Just do this very quickly. And put a big tire on them. And I get a little object here, and I can look inside this object. I'll call it a car. And here's a little behavior, car forward. Each time I click it, car turn. If I want to make a little script to do this over and over again, I just drag these guys out and set them going. And I can try steering the car here by, see the car turn by 5 here. So what if I click this down to 0? Goes straight. That's a big revelation for 9-year-olds. Make it go in the other direction. But of course that's a little bit like kissing your sister as far as driving a car. So the kids want to do a steering wheel. So they draw a steering wheel. And we'll call this a wheel. And see this wheel's heading here. If I turn this wheel, you can see that number over there going minus and positive. That's kind of an invitation to pick up this name of those numbers coming out there and to just drop it into the script here. And now I can steer the car with the steering wheel. And it's interesting, you know how much trouble that children have with variables, but by learning it this way in a situated fashion, they never forget from this single trial what a variable is and how to use it. And we can reflect here the way Julia Nishijima did. So if you look at the little script here, the speed is always going to be 30. We're going to move the car according to that over and over again. And I'm dropping a little dot for each one of these things. They're evenly spaced because they're 30 apart. And what if I do this progression that the 6-year-olds did of saying, okay, I'm going to increase the speed by 2 each time, and then I'm going to increase the distance by the speed each time. What do I get there? We get a visual pattern of what these 9-year-olds called acceleration. So how do the children do science?
Objects that you think will fall to the earth at the same time. Okay. Oh, do not pay any attention to what anybody else is doing.
Who's got the apple?
We got little stopwatches.
What did you get? What'd you get?
Stopwatches aren't accurate enough.
0.99 seconds together.
So put sponge ball.
Do the shot put and the sponge ball because they're two totally different weights, and if you drop them at the same time, maybe they'll drop at the same speed.
Drop.
So obviously Aristotle never asked a child about this particular point because, of course, he didn't bother doing the experiment, and neither did St. Thomas Aquinas. And it was not until Galileo actually did it that an adult thought like a child only 400 years ago. We got one child like that about every classroom of 30 kids who will actually cut straight to the chase. Now, what if we want to look at this more closely? We can take a movie of what's going on, but even if we single-step this movie, it's tricky to see what's going on. And so what we can do is we can lay out the frames side by side or stack them up. So when the children see this, they say, acceleration. Remembering back 4 months when they did their cars sideways. And they start measuring to find out what kind of acceleration it is. And so what I'm doing is measuring from the bottom of one image to the bottom of the next image about 1/5 of a second later, like that, and they're getting faster and faster each time. And if I stack these guys up, then we see the differences, the increase in the speed is constant. And they say, oh yeah, constant acceleration, we've done that already, and how shall we look and verify that we actually have it? So can't tell much from just making the ball drop there. But if we drop the ball and run the movie at the same time, we can see that we have come up with an accurate physical model. Galileo, by the way, did this very cleverly by running a ball backwards down the strings of his lute. I pull out those apples to remind myself to tell you that this is actually probably a Newton and the apple type story, but it's a great story. And I thought I would do just one thing on the $100 laptop here just to prove that this stuff works here. So once you have gravity, here's this: increase the speed by something, increase the ship's speed. If I start the little game here that the kids have done, it will crash the spaceship. But if I oppose gravity, here we go. Oh, one more. Yeah, there we go. Yeah. Okay? I guess the best way to end this is with 2 quotes. Marshall McLuhan said, "Children are the messages that we send to the future." But in fact, if you think of it, children are the future we send to the future. Forget about messages. Children are the future.
Will it blend? That is the question. I love my new iPad. It does a ton of cool things. But will it blend? That is the question. Doesn't quite fit in the jar, but I can take care of that. No! I knew I could get the iPad in a BlendTech Total Blender. I think I'll press the iBlend button. pad smoke. Don't breathe this. Ah, that was one tough pad.